First thing you should be doing every day when you come in here is this thing. Well, you don't need to download it every day. It's once you have it installed, of course, it's there. But when you come in every day, there will always be a question waiting for you, so you don't need to ask. I mean, unless I'm running late or, you know, roads are bad or something. You're always going to go to the room Chem Lancer when you get here, and you will always sign in with your chemical symbol. You won't sign in with your name. You won't sign in with the name of the element. You're going to sign in with your symbol because I want it to be fast. It should only be one or two letters that you're going to put in. And part of the reason is that just as somebody talked to me here before class today, sometimes their connection to the Wi-Fi kicks out or whatever. You need to get back in. I don't want you taking all this time typing in your name or whatever else. And besides, if you do that, then I'm going to think you're texting in here. And remember what we say about texters? Where should you be?
To the back row.
Yeah, you're in the back row. Yes.
But it's not valid.
The room's not valid?
Yeah, that's what mine is. I'm not sure why. I put it in
Okay. Okay. Well, that's the room name, so I don't know. So you can try a different browser or something like that. I don't know what it is, but that's part of why I don't actually count this for a grade. I mean, and when I say I don't count it for a grade, here's kind of what I use it for. I have you sign in. I have my grade book, which I have your symbol. In fact, if you probably logged into D2L, you might have seen that I already put your symbol in associated with your name. And so if somebody does poorly on an exam or whatever and comes to me and says, I've been in class every day and I look it up and I don't ever see your symbol registered, then I'm going to know that you're telling a big fat lie. And so it's not going to hold a whole lot of water. So I sort of use it for attendance in the sense that, you know, especially when I see students struggling in here, I just want to get some idea whether you're coming to class regularly or not. So, any questions? Any others? Okay, just a couple reminders, and I don't do this all semester. I do it for about the first 2 weeks, and after that, I mean, you're college students. I don't care whether you're still 16 or 17 and still in high school, or whether you're 30 or 40 years old and been out in the real world for a long time. You want to be big boys and girls or men or women or whatever, and you don't need me reminding you. So your syllabus has all of these dates in it. Go ahead and put them into your calendar so they remind you. In fact, I had a student last semester tell me that there's some sort of feature on D2L where you can actually import all those dates into your phone. I don't know if that's true or not, but if it is true, somebody, if you're a tech expert, go ahead and do it and let me know how you did it, and then I can show students in the future, and then that way you don't have to worry about importing every single date separately. We do have Mastering Chemistry, the homework quiz, that is due on Monday the 23rd. The extra credit on the 18th and the 23rd. Any questions you came up with on the syllabus? I could have swore somebody sent me an email and I said I should tell us the entire class. Who was that? Yes?
Oh, yeah, I just asked, should we bring our textbook every day?
Okay, I don't remember getting that one.
Oh,
okay.
that's on the D2L discussion.
Oh, that one. Okay, so maybe I didn't look at it this morning. So, should you bring the textbook every day? My recommendation would be yes. And one way you can do it is if you have a tablet especially, or like a laptop, you have the e-text built right into Mastering Chemistry. And so then that way you don't have to carry along an extra textbook. If you have your laptop with you anyhow, you can do that. Anybody that has a tablet or smartphone, which you should have in here, you can actually load the e-text onto your tablet device and use the same login credentials. What you'd look up is Pearson eText. Pearson eText. And if you download this app to your smartphone or tablet device, then you should be able to load up the textbook, assuming that you paid for a new textbook this semester. If you got the discounted code through the special link that I had in the syllabus for Mastering Chemistry Access, that does not have e-text access. But if you purchased a brand new textbook, it was packaged with the code and that comes with e-text access, that is available there. Anybody else? Okay, this week in lab is required safety training. Some of you already had lab yesterday, is that right? Okay, at 8 a.m. And then some of you are in lab today at 10, I believe. And somebody emailed me about that before class today, so yes, some of you do have lab today at 10 o'clock. You will be going through required safety training, and that safety training is required before participating in any other lab activities. Pre-lab quizzes on D2L must be completed with a minimum score of 2 out of 3. Now there is no pre-lab quiz for lab this week, but starting with your lab next week, you will need to complete the pre-lab quizzes with that minimum score of 2 out of 3 before you can participate in lab. Any questions on any of this? And this is a first 2 weeks type of thing. After the first 2 weeks, you're on your own. I don't talk about due dates for assignments or whatever else. I put all of the due dates into D2L, so it should prompt you if you log in. There's a calendar on D2L that shows every day what is due and your deadlines coming up. Last call. Questions? All right. So today you do need your calculators out. So if you don't have your calculators out yet, let's get them out. I did already loan out all of my extras that I have. And if you don't have a calculator with you here today, it is then your responsibility to figure out how to do this stuff on your own. Many students think they know how to use their scientific calculators. What I found out is that many actually don't know how to use their features. And so I will be teaching you how to use some of those special features, for example, with stuff in scientific notation. So we're going to start with the number 1,000. And if we look at this number 1,000, we could write this number 1,000 as 10 times 10 times 10, which is the same as
10 to the third.
10 to the third. And if we have the number 3,000, this is 3 times 10 times 10 times 10, which we could write as
3 multiplied by 10 to the third.
3 times 10 to the third. And if we have 6,700, we could write this as 6.7 times 10 times 10 times 10, or 6.7 times 10 to the third. Okay, now when we write them out like this, in fact, this first one, instead of simply writing it as 10 to the third, we could also write it as 1 times 10 to the third. And when we write it out like this, we are writing them out in what we call scientific notation. And these numbers that I gave are examples of larger numbers. We can also do it with smaller numbers. So now before we write this out in scientific notation, let's just talk about how we read this number. If we look at this number, how would we read it? This would be 1
1/1000.
1/1000th. So if we'd write it as a fraction, we'd write it as 1 over
1 over 10 times
1 over 1,000, which we already saw that 1 over 1,000 is the same as 1 over 10 times 10 times 10, which would be the same as 1 over
10 cubed.
10 to the third, which we could write then as 10 to the
10 to the negative.
negative third. And if we had a number that was 3 times as big, like this, we could then write this as 3 times 10 to the negative third. And if we had a number that was 6.7 times as big, like this,
6.7 times 10 to the negative third.
6.7 times 10 to the negative third. And these numbers are written in scientific notation as well. Now, when we look at these numbers in scientific notation, I understand that this is review for most of you in here, and for others, like if you're seeing this for the first time, maybe it's been a long time since you've done it. But one of the things I can say is that when I learned how to do scientific notation, I remember way back when learning that, and I had some difficulty keeping straight whether these exponents were positive or whether they were negative. And so there's a couple strategies that we look at when we write out numbers in scientific notation. First of all, this number that goes in front of the multiplication sign is always going to be a number between 1 and 10. And then we multiply it by 10, and then we raise it to an exponent, which is an integer value. Now, the way I learned it was like this. It's like if we look at this number, 6,700, we would move that decimal till we got a number between 1 and 10. So I move it this way, and I get 6.7. And then I was told that if we move it to the left, that means we wind up with an exponent that is positive. And that if we look at something like this, we're moving the decimal to the right, and here we come up with 6.7. And we move it to the right, we get an exponent that is negative. Now, I always had confusion with that, because what happened then is if I saw a number something like, well, let's say we had something like 3.2 times 10 to the negative fourth, then it's like, all right, if we move it to the right, that's a negative exponent. So then I come back here and I go 1, 2, 3, 4, and I come up with this answer, like 32,000, and then my answer would get marked wrong. And so that was because the rules I was confusing, 32,000 is not the right answer, is because I got the left and right mixed up with each other. So, since I've started teaching, I've observed that same thing with students and found that a better strategy would be this. And the better strategy would be that when you look at these values, these exponents are all positive, and positive exponents refer to numbers that are really big. And negative exponents refer to numbers that are really small. And that will always work. And it will tell you then which direction you move the decimal. So you don't have to worry about memorizing left to right. The fact that it's positive and negative associated to really big and small should make sense. And it doesn't matter then which direction you go. If you're going this direction, you see a really small number. If it's a really small number then, and you want to wind up with a number over here in scientific notation, that tells you that you're going to wind up with an exponent that is negative. And if you started with this number right here, and you see the negative exponent, and you were asked to get this one back over here, then that would tell us that we're going to have to move the direction that gives us a small number. And which direction gives us a small number? I'd have to move the decimal here to the left. And I'm going to move it a total of? Three places. So what I'm going to do here is I'm going to write down some numbers for you. And if I give you a number in scientific notation, I'd like for you to write it out in its standard form. And if I give it to you in the standard form, I'd like for you to write it out into scientific notation. So we'll start with this one. We have 8.62 times 10 to the negative 6. We have 92,300,000. We have 4.2 times 10 to the positive 10th. And we have 0.000049. So again, if it's given in scientific notation, write it out in its standard form. If it's given in its standard form, write it out in the scientific notation. Register your answer. Now again, I understand that sometimes the wireless bumps you off here, which when you sign in, remember to sign in with your atomic symbol. And if you have not yet done so, you should be comparing some answers along the way. Get your answers locked in. We'll count down. 5, 4, 3, 2, 1. All right, it is choice A. So there should be 5 zeros after the decimal, and then the 862. And that's because in this one we had to move the decimal a total of how many places?
6.
So we count 1, 2, 3, 4, 5, 6. To get that decimal in place, choice A is correct. Any questions on this one? Next one, we have 92,300,000. What are your choices? And we'll count down. 5, 4, 3, 2, 1. And choice B is correct. Remember that this is a number that is really big. Really big numbers are going to have exponents that are
Bigger.
positive. Okay, these are negative exponents. They don't make sense, so they're positive exponents. And then in order to get that number between 1 and 10, we have to move it 1, 2, 3, 4, 5, 6, 7 places. So we get the 9.23. Any questions on this one? All right, next, 4.2 times 10 to the 10th. First question you should always ask if you're uncomfortable or don't feel like scientific notation is your strength. Ask yourself, is the number really big or really small? So get your answers locked in. 5, 4, 3, 2, 1. All right. This one here is choice C. Remember that the power of 10 means we need to move that decimal a total of how many places?
10.
10 places. So this one here, we had moved it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This one here, we'd have moved the decimal a total of 11 places. Okay, and of course, you people over here, remember, it's a positive exponent, meaning that this number is really big. This number is really small. So remember to keep that connection together. And then the next one, 0.000049. Get your answers locked in, and we'll count down. 5, 4, 3, 2, 1. And the correct choice is letter D, 4.9 times 10 to the negative 5th. Again, this number is really small. If it's really small, the exponents are going to be negative. So whoever is up here on the 10 to the positive 5th, remember the connection is really big numbers have positive exponents. Really little numbers have negative exponents. And so in this case, we had to move the decimal a total of 5 places. So we count 1, 2, 3, 4, 5, come up with a 4.9. Any questions on these? Okay, now we are going to go to our calculators. And on the calculators, I need you, I wonder if I got these out of order. Maybe I did, maybe I didn't. Okay, on your calculators, here's what we need to do. We need to find some buttons, and the buttons you need to find are these. First button is, you need to find the EE button, which you'll find on TI calculators. If you do not have an EE button, you'll have a times 10 to the N button, or it might say times 10 to the X, or times 10 to the Y. Or it'll be a button that says EXP on it. If you have a TI 83 or 84 calculator, you actually don't have an EE button, but rather
Second and
it's a comma. So you have to do the second and then the comma to find the EE button. So find your EE button. And then the second button we need to find is the sign changing button. The sign changing button.
on TI-83 you can also do a second log, which is also 10 to the X power.
That's not the way we do it.
Oh.
No, that's for anti-logs.
Oh, whoops.
Yep, so that's why I said many students think they know how to use the functions properly on their calculator, and they don't. And so typically if we use the 10 to the x button, I wind up seeing calculation errors. So these are the buttons you should be finding. So look at your calculator and make sure you can find these. If you can't find them, ask a neighbor. If you still can't find them, raise your hand and I will show you where they're located on your calculator. But we can't do the next part if you can't find these buttons. Anybody need help locating those buttons?
Oh.
Actually,
I have no idea.
I'm very familiar with it.
You want the sign change right here? Your EE button is second.
I've gotten used to it.
Anybody else need help finding theirs? Okay. So now, here's what we're going to do. If you are using the button that says simply 10 to the x or whatever on it, that one does not work. This one is one that is used for doing anti-logs. So you want to make sure that if you have one that has the 10 to the n on it, it has a times 10 to the n in front of it, or times 10 to the x on that button. So now, when we enter these into our calculators, let's say that we want to enter something like 5.3 times 10 to the 8th into the calculator. The way that you're going to enter this is like this. You'd enter it as 5.3, and then you'd hit the EE button, and then 8. Now if you don't have the EE button, you're going to substitute whatever key is showing up here. So if you have an EXP instead of an EE, you'll use whatever that button is from row 1. And that's it. It's not a times E or times 10E. It's simply 5.3E8. Now if you enter this into your calculator, some of your displays will actually show 5.3 times 10 to the 8th. Some will show, like you have a TI graphing calculator, it'll show 5.3E8 like this. Whoever I loaned the last calculator out to right there, yours is going to say 5.3, and then there'll be a space, and then there'll be an 8 in there. So there's a lot, and I think some of them, if some of you have older TI calculators, it might have a small 8 up above. So it displays a number of different ways depending upon your model of calculator. If we want to put in something like 4.27 times 10 to the negative 5th, the way that you'd enter this one in is 4.27, then you'd hit the EE button, and then your sign changing button, and then the number 5. And so there's no times or anything that you put in there. This EE button stands for times 10 raised to a power. And if you're using the anti-log button for it, then what's going to happen is that it's going to, it will register it probably correctly, but when we start mixing up operations like multiplication and division and addition and subtraction, then it treats that button as an anti-log, and answers will wind up being calculated wrong, unless you're nesting a bunch of parentheses, and we don't want to we don't want to be doing that. So these are the ways that these would be entered in. So we then would like to go to a problem like this. If we had something like 8.6 times 10 to the 21st, put that in parentheses, and 3.3 times 10 to the 28th. First of all, if we put two quantities in parentheses like this and no operator between them, which operation should we be doing here? Multiplication. So let's go ahead and multiply these together. Now that you know how to enter these into your calculator, let's go ahead and multiply these together and see what you come up with. And so if I were to do it, I put in 8.6, I put in the EE button, 21, and then we're going to multiply 3.3, and put in the EE button, 28, And then you're going to press enter or equals, whatever your calculator does to execute an operation. Yes?
Okay, when I did the second one, the 4.271, it just came up as the same thing I typed in. I'm not sure what it is.
The second one, the 4.27?
Yeah.
Okay.
It just
They'll
came
do
up
that.
again as 4.27, even the negative thing.
Okay.
Mine did the same thing too.
Yeah.
And what is it doing?
It's just like coming up exactly what I typed in.
Yeah, it should.
It
Yeah.
doesn't want to come out like this whole thing. Like
Yeah.
the first one.
Yeah, that's okay. Yeah.
You did it correctly.
What's that? That's okay. It's registering as long as the display will show probably 4.27 E negative 5, correct?
Yeah.
Yeah, that's great. That's what that number is. That's the way that it represents. So if you're on a TI graphing calculator, if your display says 4.27 E negative 5, that is the way that the TI graphing calculators represent those values.
I thought that it listed it, like, it showed you like the phone number. Like
Um,
the other one it did.
The other one did, okay? Yeah, so sometimes it will, sometimes it won't. I don't know. Oh, there might be a setting on the calculator that will do it, but still, if you entered in like this, that means the same thing as what you just put in, okay? So, when we come back to this one here and we enter this in, and I'm going to run this through my calculator very quickly, 8.6 E21 times 3.3 E28. If you run that through, calculators are showing 2.838, correct?
Yep.
Okay. Now we want to represent this with proper scientific notation, so it'll be times
Times 10 to the 50.
times 10 to the 50th. So make sure that you can take whatever's on your display. And we'll talk about rounding. If we don't get to it today, we'll talk about this tomorrow, but this is the correct way that this one should be rounded. And again, don't get hung up on the rounding for today. We'll be dealing with rounding in here. But any questions on that value? Okay, you got to be able to get that on your calculator. If you can't, we need to figure that out for you. So let's try the next one here. Let's take 3.17 times 10 to the negative 28th and divide this by 9.07 times 10 to the 38th. So now remember how these things are entered into your calculator. This would be entered in as 3.17 EE. Then your sign changing button. 28. And of course, if this is over, what does that mean we're doing operationally? Dividing, right. So we're going to divide that by 9.07. And we'll put in the E button, and then 38. And then enter or equals. And if you've done this correctly, you should wind up with
3.5 times 10 to the negative 67.
times 10 to the negative 67. And now if you're using the times button in there and you're putting in like 3.17 times EE, whatever, or if you're using that anti-log button, then this is the one where you wind up getting that answer wrong. So go through, check your calculator. Any questions on this particular one? Okay, next up. I have a couple figures down below here, and in these figures we're going to be looking at the terms accuracy and precision. And these are two words that are often confused with each other. The term accuracy refers to how close a measurement lies to the true value. And precision we define as being the reproducibility. Producibility. of a series of measurements. So they're not the same thing. Again, accuracy is how close the measurement lies to the true value. The precision we define as being the reproducibility of a series of measurements. Now, I'm not the greatest artist in the world, but these here represent targets. And in the center of each target is a bullseye. And of course, if we're shooting targets, whether with a bow and arrow or a gun or something else, or darts, the goal, of course, is to hit the bullseye. We want to get it here in the center. And so think of the center here as being the true value. Think of the center as being the true value. And so what I'd like for you to do here now is to turn to a neighbor and ask yourself if these represent measurements that are precise, accurate, both accurate and precise, or neither accurate nor precise. So each one of them use the terms accurate and precise. So you might look at this one and say it's accurate but it's not precise. This one you might say it's accurate and precise. So use the terms accurate and precise for each one of these. I'll give you about 2 minutes here to talk these over with a neighbor.
It's everywhere. You got nothing to do with it. So
Okay, and once you have these are popping up next on your Socrative app. First one refers to figure 1. Which terms would you use? You've now had a chance to talk these over with your neighbors. They both precise and accurate. Is it precise but not accurate? Is it neither precise? Oh, excuse me. Not precise but accurate. Is it neither precise nor accurate? So let's go ahead and take about 5 more seconds. Get your answer locked in. And we will count down. 5, 4, 3, 2, 1. All right, very good. It is neither precise nor accurate. How do we know that it's not accurate? Where should it hit if it was?
in the middle.
In the middle. Okay? And if it's precise, what should happen? Yeah, we should kind of see a cluster. They're kind of all over the place. So we're not consistent. We're not being very reproducible. So we go to the next one. We want to figure out, is this precise and accurate? Is it precise but not accurate? Is it not precise but accurate? Or is it neither? So get your answers locked in here. We'll count down. 5, 4, 3, 2, 1. All right, precise, not accurate. Very good, very good. And we'll take the last one. Shots at the target. What are these? Get your answers locked in. 5, 4, 3, 2, 1. And these are both precise and accurate. They are reproducible in the
Bullseye.
bullseye, exactly. So they're reproducible there. We said that that represents the accurate value. Now, if we were to put this to a series of measurements, and the series of measurements I like to put this to, because it reminds me every semester how well or how poorly I'm doing, is my weight. And so this morning before coming here, because I knew we were talking about this today, I stepped on the scale and I came up with a value of 224 pounds. I stepped off the scale and back on again, and the next time I stepped on, I don't have a great scale, but it showed 222 pounds. So I step off, step back on again, and shows 223 pounds. So now if I were to look at these values, I want to say or ask you, what is my weight? What would be the best weight to put down here?
223, considering that's the average of those three numbers.
Okay, so we're going to put in the average. Okay? So we'd say that the average of these values is 223 pounds. But then I say, well, wait a minute. How do I know that 223 is right? How do I know I'm not 222 or that I'm not 224? Yeah.
Well, this is a precise measurement, but it's not necessarily accurate because you are within 1 pound of the average.
Well, we don't know whether it's accurate or not. All I can really say at this point is what its precision would be, and that precision would be plus or minus 1 pound. And so when I write this value in like this value here represents the precision of the measurements. And so the precision is its reproducibility. And so for me, I would anticipate that if I step on and off the scale several times, that it's going to be reproducible within that range of plus or minus 1 pound. And sometimes we refer to this as the uncertainty of a particular measurement. And typically, when you have a measuring device, we think of this last digit as being the uncertain digit. So again, if we go through here and look at these, this digit here, or the ones place, we say represents the uncertain digit. Now, when you look at a measuring device, whether it's one that you purchase for home or whether we're purchasing scientific equipment, one of the things that happens is that coming with any device will be its specifications. So sometimes you'll see specifications on, like, I bought a riding mower. It'll talk about, well, it holds 4.5 pints of oil. It holds 3.7 gallons of gasoline. And so it has specifications, and sometimes then when you're talking about like a thermometer, like I bought an electronic thermometer, and it'll say, well, it's accurate plus or minus 0.5 degrees Fahrenheit. And so those specifications will typically tell you where that uncertainty would lie in those measurements. Now, some of you were in lab yesterday, some of you will be going in lab tomorrow, and I guess actually beginning next week you'll be doing some masses of pennies on a balance, and you might come up with something like this: 2.517 grams, maybe a 2.518 grams, and a 2.516 grams. And so if you look at this set of measurements, we say, well, what would be the best way to represent this particular set of measurements? And it would be 0.517 grams as the average on this one. But if I wanted to talk about the precision of these measurements, we'd say it'd be plus or minus
1 times 10 to the third.
Okay, we'll go in the back here. We'll give somebody else a chance. Go ahead. 1/1000, which would write as 0.001 grams. Okay, so in this one here, we would say that this represents the precision or the uncertainty. And what digit would be the uncertain digit in these measurements here? Which digit in this measurement here is the uncertain one? The 7, exactly. And so it would be the thousands place, just like this is telling us, is that the uncertainty is in the thousands place. So the uncertain digits represented like this. Now, we don't, yes?
Could you also write that in scientific notation if you want to?
We could, but it's not one that would probably be, there wouldn't be any point in putting in scientific notation if the rest of the measurement's not in scientific notation.
Oh, okay.
So we want to keep the format the same or consistent between them. So what this is telling us is that these measurements have associated with some uncertainty, and very often when we look at an electronic device, we don't think about them as having any sort of uncertainty. If we look at these graduated cylinders, for example, and I'm going to go ahead and move these over to our page. So let's see, I need to cut these. Come over here and we'll paste them in. There we go. So if we put them over here now, we might look at measurements like this, and we want to figure out how would we write these out so that, and don't shout out an answer here, but how would we write out these answers so we show one uncertain digit? Now when we read these volumes, we have a curved surface of a liquid. What do we call that curved surface?
Meniscus.
Meniscus. And when we read a meniscus, we always read the bottom of the meniscus. So So what I'd like for you to do next here now is to look at these two volumes. These are measured in units of milliliters. Write down what you believe to be the volume in each of these graduated cylinders with the correct number of digits. And when I say the correct number of digits, the last digit should be an uncertain digit. So in right values, we always have all digits certain plus one digit that is uncertain. And you're going to get a chance to put these here into the Socrative app. So they'll show up, and I was told yesterday that they show up really big on the smartphones. So, and I don't know if that's true. Is it showing up really big? Yeah? Okay, so you should be able to read it with a very high level of precision there. And you don't need to give units because you're just filling in the blank and you're already given the unit. So just tell and talk with the neighbor if you need to. What do you think you'd put in? Okay, so let's get your answers locked in. We'll count down 5, 4, 3, 2, 1. And if we want one uncertain digit, that means we should be carrying this measurement out to which place? Out to the hundredths place. Because we know for sure that it's somewhere between 5.4 and 5.5. So we might write this as 5.46, 5.45. I see it as 5.46 milliliters. But remember that this last digit is uncertain, so we may have said 5.47. Any of those answers along that would be correct. But now if you're going this far out, you're taking out the thousands place, these two digits are uncertain. We only want one digit that is uncertain in your measurements. So go to the next one here. Let's see what you think this would be. Get your answers locked in, and we'll count down. 5, 4, 3, 2, 1. Uh-oh, it's not 20.34. So whoever put the 20.35, and there's several of you that did that. Why can't it be any of these? The 20.36, the 20.38? Let's give somebody else a chance here, please.
It's between 20 and 30, not 20 and 20.
Right. If we look in here, this is 20 and 30. So this mark right here is 23. This mark here is 24. So it has to be between 23 and 24. So if it's between 23 and 24, it looks like this would be about 23.6, 23.5. So those of you that put in those answers here, the 23.5, 23.4, these answers along here would be ones that are correct. But if anything that says 20 point something would be incorrect answers. So any questions on these? Oh boy, that one's kind of scary. And we often see this one with our nurses-to-be and stuff like that, so you got to pay very close attention. If you're planning one of those professions, you don't want to be overdosing or anything else in those measurements. Yes?
Thank you. So in this case, how would we write this when we wanted the plus or minus a certain uncertain digit?
Okay, if I asked you what the implied uncertainty was, and by implied, that means we're just guessing. There is kind of a right or wrong answer, but in the absence of all other data, you should assume usually an uncertainty of plus or minus 1 in the last digit. So, if we're assuming plus or minus 1 in the last digit, the uncertainty in this one would be how much? Plus or minus 0.1 milliliters. And on this one, it would be plus or minus 0.01 milliliters. So again, the implied uncertainty, by implied, it's not really a right or wrong answer. It might be plus or minus 2 in the last digit. But in the absence of that information, usually we say that the implied uncertainty is plus or minus 1 in that last digit. Yes?
So like for test, it would still be right if it was like 1 or 2 off.
That is correct. Yeah. But now, like, if somebody on this one said 5.49, that would be marked wrong, because you clearly can see that it's close to halfway between. As I look at this, it's a little more than halfway up between these two marks when I look at it. So typically the way that this would be graded is that any answers between 5.45 to 5.47 would likely be accepted. Okay? And if you were saying something at 5.44, I'd look at this and say, boy, that's more than halfway there. And so 5.44 would probably be marked incorrect. Okay? Anybody else? Okay, so now this concept that we're talking about is called significant figures. And this is where some people start being led astray. Okay? But we define significant figures like this. We define it as being all of the certain digits in a measurement plus one uncertain digit. So it's all of the certain digits in a measurement plus one digit that is uncertain. So if we go back to something like my weight, which we write like this. We said that average was 223 pounds. The way that we count significant figures is we count these two, which are certain, plus this one here, which is uncertain. We'd say that this one here has 3 significant figures. So again, this measurement here has 3 significant figures. And you're going to see me use this abbreviation, and if you're in lab with my colleagues, you use the same one. We just usually call them sig figs because it takes too long to write significant figures. Okay? And then if we went back to our penny mass of 2.517 grams, how many significant figures would this one here have? Well, which digit is the uncertain digit? The 7, right? So this would have how many? 1, 2, 3, 4 significant figures. So again, that's because this one here is the uncertain digit. And so significant figures are all of the certain digits. So 1, 2, 3 plus the one digit that is uncertain. This one here then has 4 significant figures. Again, the first one has 3 significant figures because these two are certain, and the 3 here is the uncertain digit. Go ahead.
So is there ever like a case where so basically it's just all the numbers in the number? Like is there ever a case where there's one number that's not a significant figure?
Yes. which I knew somebody was going to ask that question, which takes us to the next point. And that is where students often mix it up, because those last two we looked at should be easy for everyone. There shouldn't be any mistakes. But where we start having mistakes are when we start dealing with zeros. And we have two different types of zeros that we look at. We have ones that we call leading zeros and ones that we call trailing zeros. Leading zeros, of course, are the zeros at the front of a number. Trailing zeros are the ones that occur at the end, the back end of a number. And when we look at leading zeros, we say that these are not significant. In the case of trailing zeros, we say that these are significant. When the number has a decimal. And we say that they may or may not be significant when the number has no decimal. So it's in the case of zeros that we often have an issue. And I'm going to use a couple of examples to start these off. I'm going to start with the number 0.003 grams and the number 3.000 grams. So this is as if we were measuring something on one of the balances that we find in the lab. And we want to figure out how many significant figures there are. So now go back to the definitions and talk with the neighbor here and see if you can figure out how many significant figures would be in each of these two measurements. I'll give you about 1 minute. Go ahead. Let's see how we did here. This one's not on the Socrative app, so let's just check this one out here. How many in this first one? I hear 1, I hear 4.
4. Wait, no,
First
1.
one.
Never mind. I lied.
First one has
1.
1. So this first one has one significant figure. It has one significant figure because?
The zeros are leading.
Leading zeros. Exactly. Leading zeros do not count. So all zeros at the front do not count. We do not start counting significant figures until we get to the first non-zero digit. How many are in the second one?
1.
I hear 1. I see 4.
There's 4 now because the zeros are trailing with the decimal.
These zeros are called trailing zeros, and they are significant if the number has a decimal. Does this have a decimal? Yes. So this number would have 4 significant figures. Question?
Don't all numbers have decimal between 0 and 3?
No, they don't. If you put the decimal in like this, but let's say, so I'm going to put this in here first, 4 sig figs. Let's say that I'm talking about going from here to San Francisco, one of my favorite cities. Anybody been to San Francisco? Beautiful. Okay, been there a few times.
Does LA kind of count?
LA kind of counts. San Francisco is much more beautiful, though. So if we look at this, though, I'm telling you that it's 3,000 kilometers to San Francisco. If we go as the bird flies, it's 3,000 kilometers. Now, do you think I just made this up?
No.
Or do you think I know it?
You know it.
What do you think? You can be right or wrong. Let's say that I just made it up. Let's say if I just made it up. Then probably this is going to have one significant figure, because I know that it's about 1,600 miles. That much I know because I'm a geek. I like to look that stuff up. I'm the person that read phone books when there was such a thing. Some of you don't even know what a phone book is, right? But I was reading phone books and encyclopedias and everything when I was a kid. And so I knew then that from here to San Francisco, it's about 1,600 miles. So just doing a quick estimate in my head, that's going to be about 3,000 kilometers. Well, let's say I looked it up, and the actual resource, we took out the rulers and actually measured it using the scale, and we come up with 3,000 kilometers, then this is probably going to have 4 significant figures. And so when I put it out here as 3,000, we usually treat it as an estimate, okay? But the thing that you don't know is this. We don't know if I estimated it to the nearest 1,000. If I estimated it to the nearest 1,000, then this would have 1 significant figure. But if I am pretty good with my geography as I remember it, as being about 1,600 miles, then I would say that I'm pretty darn close out to the nearest 100. And if this is good to the nearest 100, then this measurement would have 2 significant figures. But again, if I got that ruler out and actually looked on the map and found out, yeah, it's not 1,600 miles, but about 1,680 miles. Okay, well now at this point then, if this is the uncertain digit, then this would have 3 significant figures. So that's why we say, yes, it does kind of have a decimal, but when we don't write it in, we don't know whether this estimation, how precise that is. And so as a result then, we say that when there is no decimal shown there, those trailing zeros may or may not be significant. So now there's a way around this. And one of the ways around this is to write these numbers in scientific notation. And so now if we write this number in scientific notation, we saw this number earlier today, 3,000, we can write it as 3 times 10 to the third kilometers. Remember, this is a really big number. Really big numbers are going to have positive exponents. But if we wanted to show this to the nearest 100, we could write it as 3.0 times 10 to the third kilometers. If we wanted to show it to the nearest 10, we could write it as 3.00 times 10 to the third kilometers. And if we wanted to show that this digit was uncertain, we'd write it as 3.000 times 10 to the third kilometers. Well now, guess what? This number here that has no decimal place now has decimal places. And so if we want to talk about significant figures, let's start with the top one. How many significant figures would this measurement have? It would have 1. How many would the second measurement have? This would have 2 significant figures, because when the number has a decimal, then those trailing zeros are significant. And the 3.00 times 10 to the third would have 3 significant figures. And the 3.000 times 10 to the third would have 4 significant figures. So when we want to define the correct number of significant figures, and it's ambiguous, then we put it over here in scientific notation. And that's one of the... In addition to using scientific notation for really big numbers or really little numbers, we also use scientific notation in cases when there's trailing zeros and we want to indicate whether or not those trailing zeros are significant or not. And so that's the other instance which scientific notation is used. Okay, any other questions in here? That was a good one. Okay, so now with this in mind, if we go back to these here, and sometimes students have trouble with these as to, well, first of all, why do we worry about it? Well, I teach this class in an online setting as well. Okay, when I teach this class online, those students still have to do the same labs that you guys are doing here in the lab. But now if you go in the lab, you're going to see the balances, the scales that we have in there, and each of those scales cost about $500 to $1,000. Okay, and they cost $500 to $1,000 because those balances measure out from the nearest thousandth of a gram. Okay, but I can't put those in the lab kits for the students because not everybody has $500 to $1,000 to spend on a balance in their kit. So when I send them home to the students, then I have a small portable balance which measures out to the nearest tenth of a gram. And the nearest tenth of a gram, that's a lot less precise. If it has less precision, then you don't have quite the same manufacturing standards as for the more expensive stuff. So those balances that we put in those kits cost about $10. And it's because they only go out to the nearest tenth of a gram. So the point is that those number of digits does have some factor in cost. It's going to be the same thing if you as a consumer were to go out and buy something. If you want something that is very finely made, a lot of time goes into making that device, it's going to cost a lot of money. But now in this case here now, if we want to distinguish these, why is it important in this case? Well, let's say we go back to these two measurements and we ask yourself, what is the implied uncertainty in each of these two measurements? Well, first of all, let's go back to the uncertain digit. Which digit is uncertain in this one here?
The 3.
3. And in this one here, it would be the?
The 0.
Which 0?
The third 0.
Yeah, the very last 0 right here is the uncertain digit, which is telling us that the implied uncertainty is plus or minus 0.001 grams. Now, in one of these two cases, an uncertainty of plus or minus 0.001 grams is going to be a big deal. So in one of these two measurements, that uncertainty is going to be a big deal. In the other measurement, it's not going to be a very big deal. So in which of these two measurements is that uncertainty a big deal? And why in the first one?
Because it's smaller.
This measurement here is really
Big.
small. If it's really small, relatively speaking, this amount of error is going to be really big. In fact, this is a 1/3 error. In this case here, that uncertainty is 1/3 of the size of that measurement. And a 1/3 error is a huge error. Be just like if you were driving to work here today. Now, the roads weren't great today either, but let's say that the speed limit is 60 miles an hour, like it is, I think, on some stretches of Highway 10. Okay? And so, if it was a 1/3 error, that's going to be 60 plus or minus 20. That's a huge error, and that wouldn't fly if you got pulled over by the patrol. You'd say, well, yeah, I have an uncertainty of 1/3 on my speedometer. It doesn't fly. That's a huge error. And we have a huge error, then we're going to have a very small number of significant figures. But if you look at this uncertainty compared to 3.00, this uncertainty is about 1/3000, the size of the measurement. And relatively speaking, this uncertainty is going to be very small. And when the error is relatively small, then we're going to have a whole bunch of significant figures. So when there's a small number of significant figures, the error is relatively big. When there's a large number of significant figures, the error is going to be relatively small. Now, about the only thing we have left here to deal with today is there are some cases which measurements don't have any uncertainty whatsoever. And when they don't have any uncertainty, we call those measurements exact. And if we have an exact measurement, again, this tells us that there is no uncertainty in the measurements. And if there's no uncertainty, well, first of all, what are some examples of a measurement or values that have no uncertainty whatsoever?
Kilo?
What's that?
A kilo?
What's that? Spell it, because I'm...
Kilo? Measurement of...
Oh, kilo.
Yeah.
Sure, exactly. It's possible it could if we would define a kilogram in terms of grams. Because a kilogram is how many grams? 1,000. So that would be an example of something that is exact, if it's a defined relation. And so we could say that there's 1,000 grams in 1 kilogram. It's not that there's 999.9999 grams in 1 kilogram or 1,000.00001 grams in 1 kilogram. There's exactly 1,000 grams in 1 kilogram. Exactly. So, defined relations. This is what we call a defined relationship. These here have capable, not always exact, but they're capable of being exact. Or if we'd say that in 1 foot we have
12 inches.
12 inches. That's an exact relation. And when it's exact relation, then we say that we have an infinite number of significant figures. So if you don't know this symbol stands for infinity. These have an infinite number of significant figures. And in addition to defined relationships, if I asked you how many fingers are on my hand, that number is?
5.
5. It's not 6, it's not 4. There are exactly 5 fingers on my hand. So counted items may be exact. Not always exact. For example, if I went through here and I said that there's 43 students in here, it could be that if I count fast, I could make an error. So counted items can have some uncertainty in them if you do it fast. But if we take the time and everybody numbers off or whatever here, and we find out that there's 43 students in here, that would be something that is exact as well. So if it's counted, it's not necessarily exact, but it is capable of being exact if we know for sure that we have every single person accounted for. Or if I have 5 coins in my pocket, I can count the 5 coins. That would be it. So with that in mind, we have some questions here to wrap things up today. And that is, how many significant figures in these measurements? These are the last 3 or 4 on the Socrative app. So first number is on the Socrative app here. It's how many significant figures are on 60.0500 grams. And I'm going to write these all down. So I have 60.0500. I got to make sure I get the right units. Well, it's not grams, it's meters. We've got 0.00326 kilograms. We have 246.3 milliliters. We have 3.5 times 10 to the 12th kilometers. So how many significant figures in each one? We'll give you about 1 to 2 minutes here to get these figured out, and then we'll knock them off, boom, 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 on the Socrative app. And ask questions if you have them, or ask your neighbor. We'll give you about 15 more seconds on the first one. So we'll count down. 5, 4, 3, 2, 1. There are 6 significant figures because those zeros over here are called trailing zeros. Trailing zeros do count. There are 6 significant figures. Next up, we have 0.00326 kilograms. How many significant figures in this one? Get your answers locked in. We'll count down. 5, 4, 3, 2, 1. This one here has 3 significant figures because these zeros are called leading zeros, and they
Don't count.
do not count. So we count 1, 2, 3 significant figures. Next up here, how many are in 246.3? This better be 100%. If it isn't, I have failed. As will you. We'll count down. 5, 4, 3, 2, 1.
Okay, who's that 3%?
Yeah, who's the rebel? There's 4 significant figures. There is one of something. It's not called a significant figure, though. It's called a decimal place. So it does have 1 decimal place, but there are 3 significant figures. And then the last one, 3.5 times 10 to the 12th.
You know, this one should be 100%.
some of you are starting to question it now. It's just like, I thought I knew the answer, but now I'm seeing those other choices I didn't expect. So we'll count down. 5, 4, 3, 2, 1. There are 2. Just the 2 that you see right there. 3.5 times 10 to the 12th. And the last one here. Should we continue using Socrative in this class? I just need to know. If you don't like to do it, then we won't do it. But if you do, we will keep this up. All right, we will keep it up. When you come in next class, remember to be logged into the Socrative app. Once you get in here, there will be a question waiting for you.